I am a wind-up toy. The key that winds me up is questions. Okay? If you ask a question and I don't know the answer, I will try not to tell you the answer. But if you ask me a question and I know the answer, that will start me off. If not, I have some things I thought I would talk about, but a victim. Now, keep in mind, there are no stupid questions.
How does eternal inflation break off different universes that you can't see?
Boy, is that a stupid question. Okay, so the question was how eternal inflation breaks off universes? Okay, actually that's number one on my list here. Coleman De-Luccia instantons and how infinite universes get produced inside de Sitter space. I think that's what we're talking about. Those words may mean nothing to you, but hopefully after a little bit they will mean something. Let me preface it by saying if you ask people what the standard model of cosmology is, I don't know, 10 years ago, they probably would have said a closed and bounded universe. They might have included inflation and a few other things, but they most likely would have focused on the closed and bounded, the spherical universe, the expanding balloon. There's more and more sentiment, I don't know if the right word is sentiment, let's use sentiment, for an open universe. An open universe means one which is infinite, negatively curved instead of positively curved. And part of this sentiment comes from the question that you asked, how does an eternally inflating universe break off or produce bubble universes? And what do those bubble universes look like? What do they look like from the inside? That's more important to us than what they look like from the outside, in a sense. Okay, let's begin with de Sitter space. Everybody, since I don't know what you know, I'm going to ask you at each stage to raise your hands, and please guide me, help me know where to go. Everybody know what does anybody not know what de Sitter space is? That's okay, good. So we might as well then start with de Sitter space. You mean to tell me that Arkani Hamed didn't tell you that? Oh. He said it was what? He said it 100 times, but didn't say what it was. Yeah, okay. Yeah, that was the space that was invented by Mr. Van. Well, I've used that joke to me. Okay, what is de Sitter space? All right, so the first thing is de Sitter space is the solution of Einstein's equations. It's the unique solution. Well, no, not quite unique. It's a special solution that's associated with a positive cosmological constant. Okay, now cosmological constant just means vacuum energy, and it's a solution to an equation. How many people don't know what a Friedmann-Robertson-Walker universe is? Okay, that's the place to start. I better go back a step. All right. I will not ask you how many people know what this symbol means. I can't go that far back. That's the metric of space-time, ds squared, okay? Because of the properties of special relativity, blah, 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 it begins with a minus sign, dt squared. And then if we were just in flat space, we would just write plus dx squared, plus dy squared, plus dz squared, and so forth. In an FRW universe, we can imagine that space is itself not flat, but positively curved, let's say a 3-sphere. Okay, so that means we should add a 3-sphere into here. So let's add a 3-sphere. The metric for a 3-sphere, I will write it out in detail. Here it is. That's it. Okay, and it just stands for the unit 3-sphere. Unit, I mean the 3-sphere of unit radius. But In cosmology, the radius of the universe is not expected to remain constant. It's expected to be a function of time. So there's something called a scale factor. Okay, this I suspect is familiar to a good fraction of you. And this is called an FRW, Friedmann, Robertson, Walker, Lemaitre, and how many other people I don't know, Turok universe. Bye-bye, Neil. Okay, this is the basic setup. Now, the only question is, how does A evolve with time? And that depends on the equation. Well, there's an equation of motion for A. This is geometry, so the equations of motion for A are the general theory of relativity. But when this form is plugged in as an ansatz for a solution, the equations of general relativity simplify, and you just get the following equation, A dot over A squared. You can think of this as the rate of expansion. It's the time derivative of the scale factor divided by the scale factor, so it's a rate. The rate of expansion is equal to the, there are some numbers, 8 pi g over 3, but anybody mind if I use units in which 8 pi g over 3? There are units in which 8 pi g over 3 is equal to 1. They're called Planck units. So let's just call it 1. The energy density, let's call it rho on the right-hand side, and then there's a term which comes from the curvature of space. Curved space can either be positively curved, like a three-sphere. It can be negatively curved, or it can be flat. Let's take the positively curved case, which is this case here. Then there's a minus 1 over a squared here. This comes from the curvature. If it is negatively curved, this comes with a plus sign. And if there's no curvature of space, when I say space, I mean space, not space-time. If space is itself flat, in other words, an expanding flat rubber sheet, then this isn't there. If space is positively curved, it comes in with a minus sign. If it's negatively curved, it comes in with a plus sign, which is infinitely confusing. Okay. So now, typically rho, the energy density, is something which changes as this is called the scale factor, of course, A. As the scale factor changes and grows, the energy density changes with time, generally. Energy gets diluted, so as the universe grows, typically this would decrease. Except in the special case that we're talking about vacuum energy. Vacuum energy is the energy that's stored in empty space. Well, let's go back for a second. Rho will in general depend on A. You can plug in its A dependence, and here's a differential equation for how A varies with time. Let's concentrate now on cosmological constant kind of energy, just empty space energy, vacuum energy. Let's put lambda here. And instead of calling it lambda, I'm going to call it h squared. What does h stand for? Anybody know what h stands for? Hubble. But that doesn't mean it's the Hubble constant. In fact, it's not generally the Hubble constant, but nevertheless, it stands for Hubble. The Hubble constant, which term in this equation is really the Hubble constant? First of all, is the Hubble constant a constant? No. It changes with time, okay? It's constant with respect to space in the simplest cosmologies, but it's not constant with respect to time. Which term in here is actually the Hubble, let's call it parameter? It's the left term, right? It's the left-hand term. A dot over A is the definition of the rate of expansion, but still, the right-hand side here, the cosmological constant is often written as h squared. It would be the same when A gets very big, right? When A gets very big, it would be the same. Okay, and I'm going to assume that, as indicated by the equation here, that the cosmological constant is positive. If it were negative, you'd have to put a negative thing in here. All right, so it's positive, h squared. Let's first solve it in the limit that the universe has gotten very big, in which case 1 over a squared is very small. Then it just says that a dot over a is equal to h. In other words, a constant rate of expansion or the time derivative of A is simply proportional to A itself with a constant factor, and we know what the solution of that is. The solution of that is A is equal to E to the HT. In other words, exponential expansion of space. Exponential expansion of space is the characteristic of, first of all, inflation. It's the characteristic of accelerated expansion in the current era. And it's also the characteristic of de Sitter space. The solution of this equation is just called de Sitter space. And as we see, in the limit that de Sitter space gets very, very large, it will be exponentially expanding. This doesn't quite make dimensional sense. From this formula here, A has units of a length. E to the HT is dimensionless. To make it dimensionally consistent, we could put a factor of H in here, but it's not very important. Okay, what happens when we include this term? Well, the A, instead of being E to the HT, becomes hyperbolic cosine of HT. So the exact solution of this equation, despite the fact that I'm probably getting it wrong in detail, it is the exact solution. 1 over H, I think it's actually right, hyperbolic cosine of HT. In the limit of large T, when A gets large, this is just exponential expansion. This is called de Sitter space. Okay. It has the character of being a at first it's contracting, okay? Cosh for large negative times is contracting. Cosh is decreasing. And then it achieves a minimum at which cosh is equal to 1, and then it starts to grow. So it's a space-time which looks sort of like this. It's a bounce. It's a bounce, and at the waist here, at the waist of the bounce, the minimum, A, that's T equals 0, A is just equal to 1 over H, inverse of H. So another way of thinking about H is it is the minimum size of the de Sitter space sliced along the minimum surface here. Okay, that's one way to think about de Sitter space. Any questions up till now? Good, okay. Yes?
Independent. So when you say a limit H,
I'm sorry, I'm a little bit deaf.
H is time supposed to be time dependent.
H is time independent in this equation. Okay, so that's what I was saying. This is a constant. In this approximation of just ignoring everything but vacuum energy, H is constant. It is called sometimes the Hubble constant, but it's not the Hubble constant. It's this side which is really the Hubble constant. And so this is constant. This, which is called, I'm sorry, this is confusing. This, which is called the Hubble constant, is not constant. This, which is also sometimes called the Hubble constant, is constant, but it's not the Hubble constant. I'm sorry, the equation speaks for itself. Don't worry about the words, the names.
So would it be a case we just generally replace all the H's with 3 factors?
Yes. Yeah, now if you really want to be right, it's the square root of 8 pi g over 3 times lambda. Right. Yes. It would be essentially correct in Planck units to just replace this h squared. But the reason is I don't feel like writing square roots all the time, and you know, h fits nicely as a useful parameter. Okay. Now, certainly, Arkani Hamed certainly taught you what Penrose diagrams are. Is that correct? You're kidding. Oh, God. Okay. We have to do Penrose diagrams. Am I also assuming you know everything? No. Okay, good. I'll try to keep it at this level. And if I don't, just jump up and strangle me or do something to stop me, okay? Because I much prefer that you go away having learned something than having learned everything with 0 amplitude or whatever the right word is. Okay, so next is the notion of a Penrose diagram. Now, a Penrose diagram, first of all, it's mostly useful for spherically symmetric geometries. Okay? You can think of it sometimes for non-spherically symmetric, but let's concentrate on spherically symmetric geometries. And let's start with flat space-time. If I wanted to draw a flat space-time on the blackboard here, I would put, and assume it's spherically symmetric, I would put a time axis in, and I would put a radial axis in. The radius, by definition, is positive. And then I would have to remember at every point in this space-time, there is also a hidden two-sphere, okay? Just the two-sphere that you see around you at distance r. So there would be r, t, and the hidden dimensions would be a two-sphere at every point in space, and it would be a two-sphere of constant, well, it would be constant in time, but it would be bigger and bigger as you went out. It's just polar coordinates, and spatially it's just polar coordinates, spherical polar coordinates, so at every point there's a two-sphere. This is not a Penrose diagram. This is just a depiction of flat space-time having suppressed the angular dimensions, angular directions. Okay, if we go out, oh, here are lines of constant time, equally spaced. Lines of constant radius go this way, also equally spaced. And now some definitions. No, the definitions only come after we define the Penrose diagram. Okay, what is a Penrose diagram? Penrose diagram is just a trick. Oh, no, come back. What about light rays? How do light rays, radially moving light rays which are projected at the origin from far away, how do they move? They move on 45-degree angles. So they come in like this. They bounce off the origin. Well, they don't really bounce off the origin. They just go through the origin. But having gone through the origin, they come out, begin at positive radius, and they go back out. All light rays enter at 45 degrees and go out at 45 degrees. Incidentally, if the light ray doesn't go through the origin, here's the origin, a light ray comes in at a finite impact parameter. Everybody know the word impact parameter? It just means the amount that the light ray misses the origin. Then the figure is pretty much the same, except I don't have an eraser. Is that where? Oh, okay. Thank you. All right, the figure is pretty much the same, except instead of hitting the origin, you come in, you get to some minimum distance, and you go back out. So a non-radial light ray would look like this. But asymptotically, it looks exactly the same. So one can say asymptotically, light rays come in at 45, they go out at 45. Space-like trajectories are horizontal, space-like slices, time-like axes are vertical. Now, to draw all of space-time would be prohibitive because I would need an infinite blackboard. And so many years ago, Penrose and Carter, two cosmologists, invented a trick in which you map the space-time to a finite region of space, a finite region of the blackboard, subject to one constraint. And the constraint is that light rays continue to move on 45-degree axes. Right? Now, there are a variety of different transformations you can use. It is not important to pick any one of them. More important is what the picture looks like. You compress along light cones in various ways. I could tell you precisely how to do it. You can look this up. Look up the Penrose diagram for flat space-time. But here's what it looks like. It looks like a triangle. And more than giving you the details of the coordinate transformation, let me just plot what these various things, what these various guidelines look like when transformed to here. First of all space-like trajectories, these are not space-like, these are not trajectories, these are planes, hyperplanes. But going out along a line of constant time, right, here's time. Since there's an infinite amount of time, time better bunch up as you get closer and closer to the edge of this, and it does. Okay, the space-like lines of constant time look like this. And as I said, they bunch up as you get near the extremities of the Penrose diagram. Next, the lines of constant radial position. They go up to the tip here, and they look like this. And again, there are an infinite number of them as you go out. All right, so I leave it as an exercise to find the transformation or to look up the transformation, and there are many of them which carry out this particular mapping. This kind of mapping is called a conformal mapping. Not important why it's called conformal. It just preserves 45-degree lines. So anything which is 45-degree on that is also 45-degree on here. That's the rule. Okay, that's the rule, and it can be done. That's the important thing. All right, what is this point? Some definitions. This point, which is just a point where all space-like surfaces converge. They don't really converge, but on this picture they converge. This is called r equals infinity, or space-like infinity. That's called space-like infinity. This is called future time-like infinity, and it's the place where all time axes go to. Future time-like infinity, t equals infinity. We can just simplify it. This is called t equals minus infinity, or past time-like infinity. And these lines, these are the places from which light rays come in or go out. So light rays which are oriented toward, which are projected toward the origin, come in, bounce off the origin, and go out. They can also miss, oops, that did miss the origin, I didn't mean to. This line here, which you can think of as the starting point of all light rays coming in, is called, for reasons that I don't know, scry, script I plus, no, minus, past light-like infinity, and future light-like infinity. Script I or scry. I think probably scry is the ugliest word in physics, and there's quite a few ugly words in physics. Okay, that's not the general Penrose diagram. This is the Penrose diagram for strictly flat space-time. Okay, now what does the Penrose diagram for de Sitter space look like? Very different, very different. De Sitter space, incidentally, is also a radially symmetric geometry. It can also be projected onto the plane. It can also be, this process is called compactification, making an infinite geometry and squeezing it onto a plane like this. What does de Sitter space look like? So I'll draw it for you. But before I do, let me go back to this hyperbolic geometry. Okay. All right, again, we can draw time axes. Here's what I want you to imagine. I want you to imagine the time-like axes looking like this. There are also space-like axes, which go, not space-like axes, but again, surfaces of constant time, time meaning this time over here. They look like this, and so forth. Right? It's an infinite geometry. It extends forever. It is not flat space-time. Its Penrose diagram looks quite different, very, very different than this. In fact, it's just a square. That may be a little bit surprising to you. Okay? Think about it this way. Space at any given instant is a sphere. Right? Imagine that you are at a pole of the sphere over here. This is not the North Pole would be on top, the South Pole would be on the bottom. We're at the West Pole of the sphere. Okay? We're over here. Me, I'm over here. And I look out, at different distances. I look out to that distance. I look out to that distance. And then I look out even further and further. I can only look out so far before I discover another pole. You can imagine another observer over there, your complement or your antipodal observer, at the east pole over here. Where are they on this diagram? They, of course, being observers, they live for, we'll assume they live forever. The left one is over here. Oops, I missed. The right one is over here. And so these 2 points are identified as the poles of the sphere. The vertical lines here correspond to different distances from the spatial origin. Right? The same diagram could be drawn over here. Here's the left pole, here's the right pole, and these lines here are just the vertical lines here. Notice, this is a this is a two-dimensional geometry. We're interested in four-dimensional geometries. At every point here, there's a hidden or a suppressed two-sphere, suppressed angular directions. Whether you can derive this or not is not the issue. Does everybody understand this? Okay. Now, what about these horizontal lines? The horizontal lines are just horizontal. And of course, they bunch up like that. Again, the diagram is drawn in such a way that radial light rays, now a radial light ray means one that comes in and would pass through the observer at the origin here. Radial light rays, again, are 45-degree lines. But now they don't come in from a light-like surface like this. They come in from past infinity. Let's see, this has a name. Just past infinity. And here's future infinity. Okay, past infinity, future infinity. The left pole of the sphere, the right pole of the sphere. And of course, the choice of poles is completely arbitrary. You can turn this around and put your observer wherever you like. But this is the Penrose diagram. Okay, so this is light rays. Light rays come in from here. If they happen to be projected at the observer here, they hit the boundary here and bounce off. This is not a boundary. This is just the image of the pole here. Also, there can be light rays which go this way and pass through this observer and go like that. Time-like observers, people who stand still, those are vertical axes. Okay. This is the Penrose diagram and the description of de Sitter space. Okay, now let's imagine an observer, in this case, who happens to be at the origin of spatial coordinates. In the flat space case, that means this observer is over here. And let's ask what that observer can see. That observer looks back and can see everything. I wish I had some colored chalk. I do have colored chalk. Can see everything within his or her past light cone. This is called the causal past of this point. Now, as time goes on, the observer, of course, gets later and later. His watch gets later and later. And he looks back, and eventually, given enough time, he or she will see the entire space. That's the character of flat space-time. If you wait long enough, you will see everything. Okay? You won't miss any particles or anything else. You'll see them. What about in de Sitter space? Let's look at de Sitter space and ask what the observer over at this point here can see. Again, he or she can look back. Oops, that should have gone through this point here. That observer can see everything in here. What about out here? Can they see that point? No. That's outside the causal past of the observer, no matter how late the observer gets. No matter how late that particular observer gets. Now, of course, there are other observers. Here's another observer. It just happens that this one is at the antipodal point, the opposite point on the sphere. He or she looks back and sees this region. There are observers who might wind up over here who look back and can see that point, but no single observer can see everything. This is the phenomena of event horizons. This is an event horizon for this observer. That's why de Sitter space has event horizons. Yeah. There are no dumb questions.
Because of like the symmetry here, it looks like the light cone of an immortal observer.
Right, so exactly.
Because like of the symmetry
Yeah.
and the way you drew the diagram,
Yeah.
it looks like the light cone of an immortal observer after forever is exactly half of this.
It happens. It happens to be the case.
Okay.
It happens to be the case. Yeah.
How do you use this graph to this graph? Because if we
This one here?
how to
This one.
reduce this the theta space to flat space, because we set the cosmology constant equal to that, we should reduce this graph to this graph. How to reduce this?
Oh, that's a very good question, and I'm not going to answer it. This is a peculiar property of Penrose diagrams. Often it will be the case that there's some physical parameter which varies continuously, and at some point goes to zero, and you would think you ought to be able to see how to deform your way from one picture to the other. And it often happens that the whole causal structure radically changes at that point. That happens with black holes, and I'm not going to answer the question, but it's a good question. How do you're asking, as lambda goes to zero, how do you see that this becomes this? And I'm not going to answer your question. Well, basically the answer is that this is just a very small piece of this. All right, to see that, okay. As long as there's a finite h, space-time is never flat. Just like if the Earth, no matter how big the Earth is, if the Earth is as big as it is, and we stand 6 feet above the sea level, we look out, there's a horizon. And the horizon happens to be about 3 miles away. As the Earth gets bigger and bigger and bigger, the horizon moves out, and eventually the Earth becomes flat. But it doesn't become globally flat. Small little piece of it is flat. And the same thing is true here. This de Sitter space never becomes globally flat space-time. It always looks different, but you can ask, how about a small piece which is much smaller than the inverse, h is basically the inverse radius of curvature. And it would just correspond to a small piece of this. So it would be sort of zeroing in and focusing on a small piece. But it's a good question. I'm going to leave it. I'm not going to try to answer it. But the answer is roughly what I said. Globally, the space never becomes flat as a global construction. Okay, let's see. Where were we? We were at the idea of event horizons. This is an event horizon. De Sitter space has event horizons. There are places which we just can't see. And we will never be able to see, no matter how long we wait, we'll never be able to see this question marked position, space-time position over here. Things, and incidentally, from everything that is known from the cosmology, I mean observational cosmology of the last 20 years, we at present appear to be in the late stages of in the middle stage, tending toward this kind of de Sitter space. There, of course, are other terms in this equation associated with other forms of energy density, but they all dilute away with radiation, matter, all those things dilute away. And so at late time, if there is a cosmological constant, this dominates, and this picture at late times is what our universe will look like. So in fact, we are in a world that has an event horizon. That event horizon, if you look out to telescopes as far as the eye can see, galaxies go on and on and on. There's no reason to believe that they stop. But nevertheless, there are out beyond the horizon galaxies, people, dogs and cats that we will never be able to see. The question is an interesting question. Are these proper things for scientific purposes to talk about? And I'm going to leave that because I'm not going to try to answer it. But this is the character of the space-time that we live in. But the question, all right, now we've set up, I told you, you got to wind me up, and you did. Let's come now to this question of bubble nucleation in de Sitter space. Okay, so let's make a model. We'll make a model and discuss the model a little bit. Okay, so let's begin with a theory of the energy density, the right-hand side of this equation, equals rho plus minus 1 over a squared. Let's make a model for rho. Our original model for rho was just a constant, just a vacuum energy. Okay? Let's go a little further than that. Let's imagine there's a scalar field. There's a scalar field, and the scalar field has a potential. Where the scalar field comes from, what the rationale for it is, let's not get into that now. I mean, I'm sure that Akane Hamed explained to you why there's a scalar field and why it has a potential which is shaped like this. Right? Am I right? Of course he did. Okay. Now, imagine the universe got, this of course is the potential energy as a function of a field, phi. This is phi. This is the potential energy via phi. There's also kinetic energy. If I wanted to write this in detail, I would write the potential energy plus the field kinetic energy, phi dot squared over 2. And let me assume that everything is homogeneous, that things don't vary from place to place. Homogeneous cosmology, then there would be no gradients with respect to space. This, of course, is just the kinetic field energy, phi dot squared over 2. There would be gradients of phi squared, but let's suppress those. Okay, let's imagine for whatever reason, oh, let me tell you one more thing. This is important. This is important to the logic of how cosmology works. We also ought to write the equation of motion for phi, how phi varies with time. Here's what I want to think about. I want to imagine that we started with a very high energy density, and we fell down this potential. What would happen after we hit the bottom here? Well, if it's anything like ordinary mechanics, then we would just go through the bottom and go right over the top, because we started with an energy density which was higher than the top of this potential. Agreed? If we roll the ball down a hill, down a frictionless hill, okay, we would overshoot the top of this minimum and we would never get stuck at the bottom here. Okay, that's not quite the way cosmology works. Cosmology works as if there was a lot of friction. The equation of motion for phi, which is just the scalar field equation in this expanding background. I won't try to derive it. If you just write down the scalar field wave equation in the expanding background, what do you get? You get phi double dot. That would be there in flat space. Plus, now let's write it first in flat space time. It's kind of like Newton's equations. Newton's equations would be x double dot, here it's phi double dot. What would you put on the right-hand side here? The force. The force is the gradient of the potential energy. So you'd put here minus dv by d phi. There's another term which is there because of the expansion, because A is changing with time. All right, and that other term, 3 is the dimension of space. A dot over A times phi dot. Question? I thought I heard a question, but I guess I didn't. All right, this is what you will get if you feed into the scalar field equation the metric of this, of an expanding universe, of a Friedmann-Robertson-Walker metric. Okay, what does this term look like? Looks like friction, okay? Looks like friction. And it can be very big. I mean, this is the expansion rate, of course. And the expansion rate is, winds up in the equation as a friction term. Now, this is not totally surprising. Why isn't it surprising? Well, expansion, if you have a given amount of energy density, you expect that, in other words, a given, let's say, kinetic energy of the field, you expect expansion to dilute it, and you expect the energy density to decrease. That's also what friction does. Friction takes kinetic energy and sucks it out of the system. This is not real friction. There may also be real friction of some kind, but it's not real friction, it's cosmic friction. All right, cosmic friction is there. And the result is, in an expanding universe, instead of overshoot, you may overshoot the top. If you have enough velocity, you'll get over the top. But you may also, perhaps you overshoot a little bit. It depends on whether it's critically damped, non-critically, whatever the right terminology is. It can slide down here and eventually come to rest over here because of the friction. That might not even overshoot. It might just asymptotically approach the bottom here. Okay. If the universe gets stuck at the bottom here, at least classically stuck at the bottom, then the energy density is constant with time. Okay, you're just stuck at the bottom of the potential. The energy density, there's no more kinetic energy. The kinetic energy stops because the field stops moving, and the potential energy is just stuck at the bottom. And so we can regard this as cosmological constant. We can regard this as, at least not momentarily, but at least while we're stuck at the bottom here, we can regard that as h squared. Okay? So what physics would look like if you're stuck at the bottom here would be de Sitter space. De Sitter space is what you would expect if you lived at the bottom of a potential like this. Okay? But in quantum mechanics, something else can happen. Tunneling can happen. Tunneling out of this well can happen. And you can tunnel from here to here. Let's complete our model. Incidentally, what I have in mind here is not the cosmological constant that we experience in our world, but a previous, earlier existence where the cosmological constant may have been very large. Okay, whatever very large means. Many tons per cubic centimeter. Okay, let's complete this model by having a second minimum over here where the vacuum energy is so small that for practical purposes, let's just say the cosmological constant over here was close to 0, as it is in our world. In our world, the cosmological constant in natural units is, does anybody know how small it is in natural units? Natural units means Planck units. No. That's the fourth root of it.
Oh, okay.
The vacuum energy is the fourth power of what you just said. Okay? It's approximately 10 to the minus 123. That's a small number, and I feel that for certain purposes, it might be justified to first study a model in which the cosmological constant at the end of the day is 0. So let's concentrate on that. At the end of the day at 0, sometime in the past, we may have been stuck, and I'm not going to go through all the arguments about why this type of cosmology may be the right kind, but let's just take it at face value. Here's an interesting cosmology. Somehow we got trapped at the bottom of a potential. And then, after a suitable amount of time, tunneling occurred, quantum mechanical tunneling that took us from here to here. Okay? All right. Now, depending on the height of this barrier, remember, tunneling is a rare process. It's an exponentially suppressed process. Exponential in what? Well, exponential in the height of this potential. And so tunneling rates can be enormously small. Let's suppose we're in this enormously small tunneling rate situation. Then the universe will expand many, many factors before tunneling is likely to take place. Given enough time, everything will happen. So given enough time, with probability 1, you will tunnel out of this well, but the rate of tunneling may be very small, and so on the average, it might take a lot of time for the quantum mechanical fluctuations to cause tunneling to take place. Okay, so let's suppose that that is true, that it takes a long time. By that time, the universe has grown exponentially to enormously large proportions. And so the question is, does it make sense to think of the entire universe simultaneously, all together, the entire thing, suddenly tunneling from here to here? Let's take a vote. How many people think yes, that it makes sense? How many people think no, it doesn't make sense? The no's win, and the no's are right. It doesn't make sense. It doesn't make sense to have the entire universe suddenly, which may be exponentially big, suddenly jump from one minimum to another minimum. What does happen is that small bubbles, a small bubble might form, and that small bubble form with the properties associated with this minimum, and that small bubble may or may not start to grow depending on how big the bubble is. Should we go through the little exercise of figuring out how big the critical bubble has to be? Yeah.
Different spatial configurations, or can this correspond to the same?
This is a different value of the field.
Right.
Right.
It's basically the energy density which is different, right?
Yeah, the energy density is different.
But spatially they could still be the...
Well, we're going to try to figure out what happens spatially. Okay, we're going to try to figure out what kind of thing is likely to happen spatially. The one thing that doesn't make sense is that the entire space, I don't mean space-time, I mean the entire space of this exponentially inflated world, that it all simultaneously jumps from one vacuum to the other. That's not... Yeah, why doesn't it make sense? Yeah, I hope you were going to answer.
Oh, yeah, I mean, certainly from causality.
Yeah, exactly. It's causality.
But you could imagine it sort of from that kind of picture, and I think going all the way around, like the light rays, or maybe the light rays don't go around.
The light rays can't go around. Okay. The light rays can't go around. Good. So but if you like, it is really just causality. But let's try to calculate. Look, there are constantly quantum fluctuations taking place, constantly. What kind of constant fluctuations can take place? Well, there can be small fluctuations about here, but there can also be fluctuations in which a small region of space, here it is, a small little patch, finds itself with this value of the field. This is even true in ordinary flat space-time. Quantum fluctuations take place. Usually, they just melt back into the vacuum. I claim, and we'll try to calculate it, that if this bubble is big enough, that it will start to expand. So it's kind of fun to try to estimate how big the bubble has to be in order that once it forms, accidentally, by quantum fluctuations, it will then begin to expand. So let's do a little exercise and see how this works. The background space is very, very big, so let's just take it to be enormously big. A little bubble forms, and let's calculate the energy of that bubble. Okay? Let's calculate the energy of that bubble relative to the state with no bubble. Okay? Inside this bubble here, the vacuum energy is 0. Outside the bubble, the vacuum energy is, let's just call it V. I don't want to write h squared. I'm just going to call it V. Okay? So outside the bubble, we have vacuum, we have energy V. Inside the bubble, we have energy 0. Okay, so it sounds like relative to the case with no bubble, that we have less energy with the bubble. Less energy with the bubble. How much less energy? Well, the answer is the volume of the bubble, let's call it the radius cubed of the bubble, times, there's of course a 4/3 pi r cubed, but just r cubed, times the difference of energy here and here. And it comes in with a minus sign because the energy relative to the case with no bubble will be negative. You save energy by jumping to here. So it's minus r cubed times the difference in the energy densities here. And the difference of the energy densities is just V, if the energy density here is 0. So it sounds like you always save energy, or that you always have a negative energy for the little bubble. But that's not quite right. Anybody know why it's not quite right? Surface tension at the bubble wall. At the wall of the bubble, in general, there will be surface tension, and the reason is the following. We have, let's just look at what we have. Here it is. Here's our bubble. Over here, the field is at this point. Outside, it's at this point, but as we go radially outward, we have to pass over this high barrier here. There's a lot of energy density in this high barrier. So that means there's a thin shell here with a lot of energy density, and that energy, a lot of surface energy. That surface energy can be characterized by a surface tension. Okay, so we better add to this a positive surface tension. Energy in here is positive. A positive surface tension, which we have to calculate. We calculate by solving some equations. Surface tension, and does the volume go there? Sorry, does r cubed go there? R squared. Okay, now let's plot that. Let's plot that as a function of r. I'm running out of blackboard. No, I'm not. Let's plot it as a function of r. R being the radius of the bubble. Okay. There's a term which is minus r cubed v plus a term which is tr squared. For small r, this one wins. R squared being bigger than r. Is that true? R squared? Yeah, r squared bigger than r cubed for small r. So it starts out this way, quadratic. For large r, this one wins. And there's some maximum someplace. If the bubble that forms has a radius which is smaller than this over here, then then the surface tension wins, and it'll just squeeze itself down. Surface tension will squeeze it back into the original vacuum, and it will disappear. If the bubble which nucleates is over here with a radius bigger than this critical radius over here, then it slides down this way and it starts to expand. Okay? It starts to expand. There's a kind of force on it. The force on it is due to the difference of energies in the two vacuums, and it accelerates. So there's a domain wall which, if the bubble that nucleates is large enough, that domain wall begins to accelerate outward. And we have to solve some equations to see this, but the acceleration is such that very, very quickly the domain wall approaches the speed of light. It never quite gets there, but it very, very quickly gets very close to the speed of light. It's like a particle with a uniform force on it. Yeah.
Tunneling is happening.
Say it again.
During this process of tunneling,
Yeah, this is the process of tunneling. Okay,
Right.
the process of tunneling is the quantum fluctuation which creates a bubble bigger than the critical, or of size the critical radius or bigger. So there's constantly bubbles forming due to quantum mechanics. Quantum mechanics is all over the place. Little bubble forms here, little bubble forms here, little bubble forms here. But every once in a while, a bubble of large enough radius will form, and under those circumstances, it will have enough volume energy to overcome the surface energy, and will start to grow. And you were going to ask a question. I interrupted you.
now when this bubble is forming, there is an initial state and there is a final state, I guess. The initial and the final state, I was going to ask you, how are they spatially similar or different?
Okay, well, that's where we're going now. That's where we're going now.
Because you assumed here, it seems in your equation, that the R term for the initial and final state, when you're calculating energy differences,
Yeah.
is the same, doesn't sort of change.
All I calculated now, incidentally, this is exactly the same calculation you would do if instead of talking about cosmology, you talked about metastable water or any metastable phase in condensed matter physics. Anybody know what ice 9 is? Okay. Ice 9 is a metastable form of ice which melts at 114 degrees Fahrenheit, I believe. It's a very dangerous substance because it has lower energy than ordinary liquid water. And if a small little droplet of it forms, if the droplet is big enough, it will start to grow and eventually swallow up all the oceans and everything else. Okay? Now, do you believe that? No, of course you don't, because it would have happened by now. But it's the subject of a story by Kurt Vonnegut called Cat's Cradle, which has a lot of good physics in it, incidentally. Anyway, yeah, this is the way you would write down exactly the same equation for the nucleation of a bubble of ice 9 if the ice 9 has lower energy than ordinary liquid water. This is precisely the, and in that case, it wouldn't be quantum fluctuations which would drive it, it would be thermal fluctuations. Every once in a while, a group of molecules would get together. Oh, and the real thing, of course, is that you can really cool water below the freezing temperature. If you do, it becomes metastable. If you put a little bit of ice into it, that ice chip will begin to very rapidly expand. But even if you don't put a foreign piece of ice into it, you wait long enough, just by accident, by pure thermal fluctuation, enough molecules will arrange themselves accidentally into a crystal of ice. And once that crystal is big enough, it will start to expand. So it doesn't really take a foreign bit of substance to drive it. But as you might expect, it takes a long time for such an unlikely thing to happen. Same thing here. It takes a long time, but eventually, given enough time, it will happen. Okay, so now we come to the question of spatially and space-time sense, what this process looks like. The nucleation event, let's say the center of the bubble, the critical bubble, is located at some point of space and some point of time. What point of space and what point of time, that's quantum mechanics. It's uncertain, but when it happens, you'll know it, especially if you're nearby the thing. All right, so let's arbitrarily put the center of the bubble right at this pole of the sphere. In other words, the bubble nucleates somewhere along this axis, where every time is the same as every other time, so let's put it over there. That's the nucleation, and then the domain wall begins to expand. The domain wall expands, and eventually, in a very short time, gets to be close to the speed of light, asymptotically gets to the speed of light. And so, without too much error, I'll just draw it as a outgoing shell with very close to the speed of light. In here, that's the interior of the expanding bubble. And there, the vacuum energy is 0. Outside, the vacuum energy is whatever it was. Right? This is the phenomena of bubble nucleation that creates a patch of space, an expanding patch of space that has the properties of whatever goes on here. Now, we're not quite finished. If the cosmological constant is 0 over here, that means the space inside here is flat space-time. Cosmological constant 0, that's flat space-time. So what goes on in here must resemble this picture. If you want to work it out in detail, well, in detail it's a little bit complicated, but roughly it's a matter of cutting and pasting. Are we supposed to be someplace? What time are we supposed to go to? Okay. Just tell me when you get bored and I'll stop. All right. One of the tools of general relativity is the scissors, where you cut and paste different geometries together along a boundary, and in this case the boundary would be this accelerating domain wall. On the outside here, what goes is the de Sitter space. On the inside is this flat space-time. Right? And notice that to a high approximation, we can take this domain wall to be light-like. So on this side of the picture here, we should also draw a light-like surface. Now, on this side of the picture, we throw away the piece that's unphysical. That's the piece in here. In this picture, we throw away the outside, and we keep the inside. So it would look something like this. This would be the Penrose diagram for a bubble nucleation. And here is the universe with zero cosmological constant. Now it's kind of interesting to ask, I'm going to slow down here. I may be going too fast. Stop for questions. Yeah.
Are they competing with each other? Because there's one is expanding into the other universe. So
Yes, that's correct. This one is expanding into this universe. In a sense, they are competing, but let me tell you, the competition is not quite between these two vacuums, but between two rates. So let's talk about those two rates, the two rates which come into it. If we were talking about condensed matter, and we had an infinite sample of metastable water, there wouldn't just be a single bubble nucleation, but if you go out far enough, there'll be another bubble nucleation somewhere, and eventually they will all expand and come crashing together. And when that happens, the entire sample, the entire infinite sample, will find itself in the stable phase. Right? It's not just one bubble that expands, but depending on the decay rate, you may have to go out a zillion miles before you find another bubble expanding. But sooner or later, you'll find another bubble expanding. Okay, that's different than what goes on here, and the reason is because in this vacuum here, it's inflating, exponentially expanding, okay? So the exponential expansion, which takes place here, means that if another bubble forms, let's say a bubble forms over here, the region in between is exponentially growing. And for that reason, this domain wall may never catch up to this one. And the region in here will stay an inflating region. If the decay rate is small enough, there will always be places which are left undecayed. All right? Just because these bubbles are separating from each other, they're expanding, separating from each other, because the space is growing in between them. And that's what's called eternal inflation. Yeah.
Downward from the diagram,
Yeah.
the timelines get closer and closer together. So it seems like
Yes. You're asking the right question.
if a nucleation occurs on the bottom, yeah.
You're asking precisely the right question. You're asking, if it can happen here, there's an infinite amount of time down here, why didn't it happen in the remote past, and why didn't it happen all over the place in the remote past? Okay. Nobody knows the answer. It's generally conceded and by everybody who thinks about this eternal inflation that you'll have to imagine an initial condition that this full picture is unphysical. Incidentally, the same is true of a black hole. Half the Penrose diagram is unphysical. You have to imagine that the contracting phase here is really replaced by something else, and you don't know what. And this is a point that's been made over and over by Alan Guth and other people, that this de Sitter region here still necessarily needs some kind of initial starting point that's outside the range of these considerations. So we first throw away this. We first throw away this. Don't ask why, but we had better throw it away. Otherwise, our universe would have decayed in the remote past. And roughly speaking, you can imagine starting at the center of the waste here. Okay. Does this make sense? Who knows? But that's the picture. So you've got to throw this away. But having thrown this away, we can now study the bubble nucleation phenomenon in this manner here. Okay, because the space at late times is exponentially inflating, the distance between points growing exponentially, bubbles can nucleate and not crash into each other. There are two, okay, so now comes the question. What is the competition which determines whether the entire sample will crash the same way the condensed matter physics works, or whether it will continue to eternally inflate in the regions between the bubbles? There must be some competition. And what is it that's competing? Well, there are two rates involved. The first rate is the rate of expansion. This Hubble, this is the rate of expansion. This is h squared. No, sorry, this is the square of the rate of expansion. So h is itself a rate. It's the rate of expansion. A rate means the time derivative of something divided by the something. Okay? So there's the rate of expansion on the one hand, and the other thing is the bubble nucleation rate. It's a rate. It's a tunneling rate. Okay? If the bubble nucleation rate is sufficiently much smaller than the expansion rate, then expansion wins, and the transition to the minimum here is never completed. It's never completed, and there are always inflating regions in between, even though there may be an infinite number of bubbles nucleated. But the final question is, let's agree that we live in a vacuum, that we live in a region like this. What does it look like to us? What does it look like from the inside? From the outside, it looks like an expanding bubble. What does it look like from the inside? Well, you might think that what it looks like is an expanding, let's imagine the domain wall has some physical property. It's a reflector. It's a mirror. That's just it may or may not be a mirror, but let's suppose it's a mirror. Does that mean that we can look out at space and see our reflection in the mirror? No. Of course, to see our reflection, we have to send the light ray out. It's got to bounce off the mirror and come back. Okay, let's look at this. We're over here. I'm right over here, for example. Right? I send the light ray out. It never gets to this domain wall. It just goes out to here. So the answer is no, I can't see my reflection in the mirror. Okay? So you don't see the domain wall directly, or at least you can't see it by trying to illuminate it and see the radiation that comes back. The interesting question is, after the tunneling, before the tunneling, the field phi is constant. It's just sitting at the boundary here, at the bottom here. It tunnels through, and it doesn't quite tunnel right down to the bottom. In fact, it tunnels to some point on the side of the potential here, and then slides down to the bottom. So there's a period in here of decay of the field till it gets down to the bottom. It's an interesting question to ask, what are the surfaces in this diagram that correspond to lines or surfaces of constant field? Okay. In particular, in here. The field decreases as you go up this line here, if you're sitting at the center. It also decreases if you're sitting over here. All right, I'm going to draw for you what the lines, now this requires some mathematics. It's not very difficult mathematics. It requires some mathematics to work out. But the surfaces of constant field look like this. So the field here is over here. Then there's a jump through the domain wall, and it gets to be over here. That's the jump across here. Having gotten there, it slides down. And it slides down on surfaces which look like this. That tells you what somebody sees in here. They see a world which is homogeneous, everywhere is the same, but everywhere is the same on surfaces, space-like surfaces, which are these slices here. Okay. How big is each slice? How big is each space-like slice here? Is it finite? Is it infinite? Right. Well, for that, you have to remember what happens up at t equals infinity here. What happens to the metric at t equals infinity? It exponentially gets big, right? Exponentially diverges. So the metric up here is exponentially big, and in fact, it's got to be continuous through this junction here. So as you ride along one of these space-like surfaces here, the metric gets bigger and bigger and bigger, and the space-like surface, the space-like distance from any point to the boundary here is infinite. Okay. The geometry inside this bubble is not a closed universe, but an open universe with hyperbolic, negatively curved space. And it's infinite, and so the observer inside this bubble, even though he's inside what at any given instant is a finite, any given instant from the outside we draw some instants, and we see at any time the bubble is finite, although it's growing. The observer on the inside, what the observer on the inside reckons as time, is these surfaces of constant field. He or she says the universe is infinite. It's infinite, open, negatively curved Friedmann-Robertson-Walker universe. So this is a peculiarity of this kind of bubble nucleation, that it inevitably leads to a world which is not the old-fashioned kind of balloon world, but the negative curved version of that, in which space is infinite, negatively curved, sort of a saddle surface that goes forever and ever, saddle surface being the negatively curved surface. Okay, I'm going to quit there. That I think did I answer your question?
Largely.
Largely. Which piece didn't I answer?
I was also wondering, why would all the different universes have slightly different values of the quantum constant?
Well, okay, that of course depends on this was a model. This was a very, very simplified model of what has become called the landscape of vacuum. There may or may not be, string theorists think there are many, many multiple minima like this. So, there might be another minimum over here. No, I want to put that lower. If you somehow got over to here, you might tunnel this way, you might tunnel this way. If you tunnel this way, what you would see would be different than what happens if you tunnel this way. So there could be other, not only could, but there would be other bubbles with different properties. Depending on how rich this landscape is, the richness of this collection of bubbles up here can be arbitrarily rich. So, did that answer it?
Yeah.
Okay, good. There should be a referee here. Okay, I'm going to stop on the right and work to the left.
How does the Big Bang factor into this? Is that
Yeah.
are you explaining that by this
Yeah.
tunneling?
Yeah, I mean, I'm not going to try to answer one way or the other where it explains it. Where is the Big Bang in this picture? The Big Bang is along here. This whole surface here is t equals infinity. This is the Big Bang. Somebody looking back and looking sort of the domain wall is looking back and seeing the origin of the Big Bang. So the domain wall doesn't look like a domain wall, it looks like a Big Bang. Is that yeah, okay, so I was working from your left to your right. Yeah. Yeah, good.
Me?
No.
I have a question. I'm all the way on the right though. Or
You're on your right.
I'm on somebody's right, yeah.
Yeah.
So this is a model for our universe, right?
This is a model of
Yeah.
some universe.
Okay. And so
It's a model of some multiverse.
okay, but our universe would be one of these bubbles.
Our universe is one of these models.
Right,
This
and
is
we
one of
have-
these linguistic glitches. The word universe was not intended to have a plural.
Right.
But,
And so when we tunnel from that high value of
Yeah.
a vacuum
Yeah.
to this low value, and we ride down the slope afterwards, is that inflation happening?
yeah, okay, good. Ooh, very good. Yeah, exactly. Where does normal inflation take place? This picture doesn't require any fine tunings. It just requires a bunch of minima.
Yeah.
Okay? Inflation would take place on a broad plateau in here.
So
Now, this sounds crazy. Why would there be such a broad plateau? I'll come back to it in a minute. But just suppose there was a broad plateau. Remember, friction slows you down. So you get down to this broad plateau, and you inch along here and creep along here slowly, with the vacuum energy being approximately constant along here. That's conventional slow roll inflation. And where it takes place is in here. Until you get to the end of the plateau, where you fall off the plateau down to the real bottom. And that would be late times up here. Now, you say, why should there be such a crazy potential?
that's yeah.
This, nobody knows, but there is a possible answer. You may either reject this answer out of hand, or you may accept it, depending on how you feel about anthropic considerations. But if you didn't have this period of slow roll inflation here, okay, first of all, back off a minute. There are three possibilities for ordinary Friedmann, Robertson, Walker cosmology. All right? There is positively curved, negatively curved, and zero curved. Those correspond to three Newtonian situations for stuff flying out from a center. What are the three situations? The three situations are any point relative to the sphere of material inside that point can either be at greater than, less than, or equal to the escape velocity. If you're above the escape velocity, everything just continues to go out. If you're at the escape velocity, you asymptotically slow down, the universe asymptotically slows down, and but still logarithmically continues to expand. If you're below the escape velocity, then you crunch. Okay. Those are the three possibilities. Now, what do they correspond to in terms of general relativity? They correspond to the closed spherical universe, the spatially flat universe, not space-time flat, but spatially flat, and the hyperbolic negatively curved universe. Right? This is a hyperbolic negatively curved universe, and it means, in effect, that everything is shot out with greater than the escape velocity. Okay, now that's fine except for one thing. If you're too much above the escape velocity, even patches of space will not turn around and form galaxies. Okay? So having too much of this negative curvature will simply wipe out the ability of the primordial, very, very small density inhomogeneities to turn themselves around and form galaxies, to form structures, planets, galaxies, and so forth. So somehow you have to get rid of that negative curvature before structure formation happens. How do you get rid of curvature? By inflating. You inflate away curvature. So one might say that, well, there's a zillion different vacuums. Some very, very small fraction of them might have plateaus like that. But in order to have structure formation, in order to have planets, galaxies, and so forth, we might as well focus on the vacuums which have this kind of plateau. That's a logic. Whether it is the right logic, well, I think it is, but you know, there's, there's plenty of dispute about that. But no other explanation. Dispute, but no explanation, yeah.
And it is similar or analogous to the glass transition.
The glass transition. I would say this is not like the glass transition. It's true, the glass transition has many, many minima. That's what you're thinking about, the fact that glasses have many, many minima?
Yeah, and then leading from that fact, in this multiverse, there could be inflating universe. There could be universes which are not inflating.
Okay.
Sort of kind of.
It may be that a glass which happens to inflate might be like this. Let's talk about inflation, or any kind of exponential expansion, how to think about it. How to think about it in intuitive terms. Let's come back to the balloon picture. All right. Balloon is expanding. What happens to balloons? Let's imagine you have a balloon which you're blowing up in such a way that it exponentially, I think we have to go, don't we?
For a long, long time.
Okay, I'm here for some period of time.
Yeah.
I'll probably come and have lunch with you guys. It's more interesting than having lunch up there, so.
Yeah, come and see it.
I'm glad I've been asked to